Hello, physics students. Welcome to part 2 of mental exercises, creating and understanding graphs. So you already printed this out. We're going to be using the same sheet, only we're going to go on to the acceleration part. And I'm using, once again, a motion detector, but this time I want you to practice creating graphs with acceleration. And we did with the Spark Labs, when we studied acceleration, we were dropping things. But for this activity, it's too fast, right? By the time I walk over here and start this, you know, the experiment is over. So to study acceleration, what I'm going to do is use a ramp, which still makes acceleration caused by the force of gravity, by the way, but at a lesser acceleration than if I drop something, okay? So it'll allow the graphs to be made at a slower rate so we could watch them being made once again in real time. So we turn to right here, page 2 where we left off, and it says acceleration, number 1, consider a cart rolling freely down a ramp with a motion detector at the top of the ramp. So that's what I've got here. Okay, and as I said before, don't just wait for the graph, otherwise you don't have any fun with this, right? Yeah, right, you're thinking fun. But make a prediction. Doesn't matter if it's wrong. It'll help you learn to try and think through it yourself, and then I'll show you the actual graph so you could see what it really looks like. All right, so again, I'm going to start the ticking, and then we're going to graph this now, okay? So notice it's starting by the motion detector and it's going to go to the bottom of the ramp. I'll pause the video, give you a chance to make a prediction. Okay, let's take a look. Maybe a little higher. Let's see, maybe like that. All right, there it is. Again, just like in the last experiment with a car, battery-powered car, we want to look at the ideal. This is the result of me trying to rush over and let the car go. So we want to start our axes right here. And what you should observe is that is not a straight line, okay? It is a parabola. If I put a meter stick here, you see definite curvature there. All right, so what I want you to do is, well, I'll make some kind of prediction and then I'll sketch in the actual. Okay, so this is what I want you to draw for the actual. So I made a prediction, straight line up. It was not correct. It's really this, okay, parabola. Now, let's talk about why. So first of all, it's moving away, okay? It started close, so we start near the origin. If it started away from the motion detector, we'd start our graph here. Why does it curve instead of a straight line? And why does it curve this way instead of curving that way? Well, remember, the slope of this line is the velocity of the object, okay? So in the beginning, you could see it physically. You could hear the sound of the wheels. It was going slow here, and then it was fast at the bottom. So how do I begin a graph slow? I've got to begin it by drawing horizontally. But as time goes on, like right here, see? The curve has more of a steepness here. How about here, later? The curve is even steeper. Over here, when it was at the bottom, even steeper. So the velocity or the slope of this has to continually get more and more, and that implies a curve speeding up, okay? Has to be. Now, I'm going to pause the video to give you a chance to sketch the velocity graph. So go ahead and do that now. Okay, let's see what it looks like. All right, so again, we got to kind of think about fixing this up. So What we've got here is axes like this, and what you should see is a straight line up, okay? Starting at the origin. So one way to think about, oh, let me just show you. Okay, so my prediction was like this, like the last graph, but it's incorrect. It should go like this, okay, starting at the origin and rising upward with a straight line. Now, why? Well, first of all, it's going to start, let's do physically first. Physically, it starts here and it's moving slowly and goes faster, faster, faster in the positive direction. So we start slow at 0 velocity and we increase in the positive direction faster, faster, faster. But in the last set of graphs, they were all like this because the velocity was constant. This is now increasing positive velocity. That's physical. Mathematically, what we're plotting down here is the slope of this curve. And you could see the slope of the curve is near 0 here. And then the slope of the curve gets greater. See how my pencil's getting steeper? Pencil's getting steeper. Pencil's getting steeper. So the velocity keeps increasing, so the slope keeps increasing. And that's what this graph is, the slope of this graph. Acceleration graph. Again, don't wait. Make a hypothesis. I'll pause the video to give you a chance to do that. Okay, let's see what the computer shows us. Probably going to look a little messy. Yeah, a little messy, but what we're interested in is the pattern. Again, this is me sort of nudging in the beginning. We want to start our axis here, and it's straight across positive. Okay? So maybe you had something like this for a prediction, but it really is like this. So this was my prediction, incorrect. The correct one is straight across like this. Constant acceleration. And a lot of people, you know, this is a very common mistake. They'll say, they'll see this thing going down the ramp and they'll see it, okay, it's going faster, faster, faster. And they say, oh, I know, that's an increasing acceleration. And so they make the acceleration graph go up like this. What you're doing is you're confusing velocity and acceleration. Velocity is how fast you're going. And yes, this is going faster and faster, but the acceleration is the increment your velocity goes up by every second. And if your speedometer goes 0, 2, 4, 6, 8, 10, you're going faster and faster down the road. But what are you adding to the velocity, to the speedometer every single second? You're adding 2. You went from 0 to 2, that's 2. Then you went from 2 to 4, that's 2 acceleration. Then you went from 4 to 6, that's 2 acceleration also. So kind of tricky, okay? The acceleration is how much you're adding to the velocity, and in Regents, accelerations are always constant. We only study constant accelerations. We never study increasing accelerations or decreasing accelerations. It happens in real life, but it's too complicated for the Regents. So acceleration graphs should always be like this, 0 or negative. Okay, enough there. Let's go on to the next one. Step 2. Consider a car rolling freely up a ramp with a motion detector at the top. So what I'm going to do is I'm going to hit the thing to click. I'm going to run over here, and I'm going to go like this. Well, and I'm probably going to mess up like a bunch of times. I need to push it a little hard. I'm going to go like this. And then I'm going to stop it like that. So I gave it a brief nudge at the bottom, and then it sort of rolled up, and then I'm going to catch it here. Make the prediction, okay? Okay, let's have the computer generate these graphs. Okay. put this one away. Let's put that one away. And let's see how good I am. Okay. Not good. All right, we'll do it again. What I'm afraid of doing is smashing the motion detector. That wouldn't be good. Push it too hard, it's going to slam right in, right? So let's try again. Oh, that might be it. All right, that was actually perfect. Amazing for me. Okay. All right, so again, we've got to idealize this. So the axis is here. This was me running over and the thing just waiting there for me, right? And then I gave it a shove. So we're looking at a curve like that. And it is a curve. Again, if I put the ruler here for reference, we can see the curve. So maybe you predicted something like this, but the actual is like this. So again, I hope you're making predictions. I made one. I was wrong again. I'm wrong every time. Geez, boy, I'm bad at this, right? So it curves down like this. Now, you might be wondering, why not like this? Okay. Why does it, instead of doing this, it curves down like that? Let me explain. So first is a physical explanation. I'm starting far away from the motion detector, so I don't start at the origin of the graph, I start far away. That's the first thing. Why not this? Why that? Because what I'm doing is I give it a brief burst of energy and it's going very fast toward the motion detector. And remember, the slope of this line tells me how fast it's going. And if I start it curving like this, I'm starting it with a slow velocity. That means it's starting slow down there. And as it goes up the ramp, it's going faster and faster because this is getting steeper. And that's not what happens. It starts fast down there, and then it slows down to a stop up here. So it has to curve down like that. Okay, no being lazy. Sketch a velocity graph. I'll pause the video, give you a chance to do that. Okay, so let's see what the computer has in store for us here. Okay, so again, we've got to idealize this a little bit. So the axis is here, and you're starting down here and going up like that. So maybe I had something like this, but the real graph is like this. Okay. So here, wrong again. It's okay, right? We're just making hypotheses. This is the actual. So I don't know what you had, but I was this, but I drew the actual right here. Now, why did it look this way? Again, there are two ways to think about this. There's the physical, and then there's the mathematical. So the physical is that down here, I shoved it in the negative direction. And it's moving very fast right here in the negative direction. So it doesn't start in the positive like I drew it in my prediction. It starts negative, going backwards. And it's slowing down on the way up, and at the top it stops. So that's a physical interpretation. How about a mathematical one? This graph is the slope of this graph. And what you could see is right here, the slope is very negative, right? That's a negative slope, that's a positive slope, that's a zero slope. So this is very negative, so the graph's going to start here. And then the slope continues to be negative, but it gets closer to zero, closer to flat. So it's less negative, less negative, less negative, and now it's zero. So that's the mathematical. All right. Go ahead and make a prediction for the acceleration. Now, I keep saying don't be lazy, make a prediction, but maybe I'll worry you a little bit. Most of the time, Most students get this one wrong. This one is really tricky, okay? So give it a shot. Maybe you can brag later that I got the tricky one right, so give it a shot. Okay, let's see. All right, so again, this is all me giving it a shove, but we're starting here. Positive acceleration. And what a lot of people might think is, wait a minute, this is going up and slowing down. That should be a negative acceleration because it's slowing down, okay? How is the, oh, by the way, let me show you the idealized graph. So it would look like this. Look, this time I was actually right. Oh, that's good. I pat myself on the back. But the actual is straight across positive, okay? So why is the acceleration positive? Well, remember, positive acceleration doesn't always mean speeding up, and negative doesn't always mean slowing down, okay? What it is that if your acceleration and velocity are the same sign, you're speeding up. If they're opposite sign, you're slowing down. So think about this. I'll make up a number. I got an acceleration of -10. I got a velocity of -10 in the beginning. How do I get to 0? Do I add -2 every time and go -10, -12, -14, -16? No, negative acceleration of -2 is the wrong thing if you want to get to 0. If I've got a -10 velocity, what I have to add to my velocity every second, which is what acceleration is maybe like +2. +2, right? So my velocity is -10. Then I add 2, I get to -8. Then I do +2, and I get to -6. +2, -4. +2, -2. +2, 0. Every time I had to add a positive number to my negative velocity to get me to 0 velocity. Positive acceleration, slowing down, okay? The other way to think about it mathematically is actually easier. If you look at this velocity line, what is its slope? Because the slope of a velocity graph is the acceleration, okay? And this is a positive slope. Same as this, negative slope, right? This is still a positive slope, okay? So that's it. All right, last one. Consider a car going up, then down with a motion detector at the top. So I'm going to start the ticking. Tick, 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 tick. I'm going to give it a shove, and I'm just going to let it go up and back down, okay? Make a prediction of the displacement graph. All right, hopefully I do this on the first try. Uh-oh, something's wrong with our motion detector. Let's see. And that was like a nice push too, by the way. Terrible. Okay, let's see what went wrong. All right, I don't know. We'll just try again. Murphy's Law. What went wrong is I had a nice push, right? So the machine didn't like that. It wanted me to mess up, right? So. Well, not as good, but I guess we'll have to go with it. All right, so first one was better, but what are we going to do? All right, so what it is, you put your axis here, and it's basically an upward parabola. Okay, so prediction, maybe you had something like this. Okay, so I had something like this, incorrect, not bad. I did know that it was starting far away, came close, then went far away again. But what it really is a nice smooth parabola, okay? So, physically, we can interpret this by saying it started far away, not there. If it started here, the graph would start at the origin. It starts away from the origin because that's where it started. It gets closer as it's coming up, and then it gets further away. And it has to be a curve because it's accelerating, not my straight line. That would be constant velocity, constant velocity. The other thing is it doesn't curve like this with a sharp point over here because it has to start not slow and get faster. It has to start fast, get slow at the top where it just creeps up to the top, and then it goes faster and faster away. So that's the graph. All right, make a velocity prediction. Okay, I'll pause to give you a chance to do that. Okay, let's see the graph. There it is. Starting here, negative, rising up. Okay, so I made an incorrect prediction like this. I don't know what you did. Maybe you got it right, but that's okay if you didn't. But the actual goes up like this, straight line. Okay? So, again, two ways to interpret this and to generate this. One is physically. I shove it this way. That means my velocity is negative in the beginning because it's going toward, not away. This would be positive. So it starts negative. On the way up, it's slowing down, getting closer to zero velocity. That's the peak. And then it starts going in the forward direction, positive, ever so faster. Okay? So that is the velocity graph. Now, that's the physical. Mathematically, this graph is the slope of this graph. In the beginning, we're at a high negative slope. We're not a positive slope, we're not a zero slope, we're a negative slope. Then the slope gets less and less, and then right here it's flat, meaning zero slope. And then the slope starts getting positive, and it has maximum positive slope right there. So that's the mathematical thinking behind this graph coming from that one. Last one, acceleration. Give it a shot. Make a prediction. Okay, so let's see what the computer generates right here. Straight across positive the entire time. So straight across positive. So again, you had some prediction. Maybe this is what I'm going to have. I'm going to have something off like this, but so what I had was this, which is incorrect. It's actually straight across positive. What maybe I was thinking incorrectly is that it was slowing down. That's a negative acceleration. And then it started speeding up. That's positive. But it's incorrect. It was positive acceleration the entire time. While it was slowing down, while it was speeding up, positive the entire time. All right, so how do you reason that out? First, physically. The gravity is always, whether it's rolling up or rolling down, the gravity is always pulling it down the ramp away from the motion detector. We're going to learn in the next unit that that's basically the acceleration is the way the pull is. That's the direction of the acceleration. So it's pulled down the ramp in the positive direction the entire time while it's rolling up, while it's rolling down. So that's kind of like a physical. Or you could think, I go from negative velocity to zero. So that's a positive change. Negative 10 to 0, that's a positive acceleration. Then I go from 0 to positive 10. 0 to positive, that's also a positive change. So another way to think about it. And the last one is a mathematical way. Acceleration is the slope of the velocity graph. And look at this graph. This line has a positive slope here. All right, it's in the negative, but it's sloping positive. And then it's still sloping positive. So sloping positive, sloping positive. Okay. All right, so I hope you had fun, as much as fun as I did with the mental exercise in creating and understanding graphs. There's some questions at the end. I'll put it in the Google Stream whether I want you to do them or not. Right here, I don't remember what else I have going on in the unit plan. So I'll put a note and I'll let you know if I want you to do those questions at the end. All right, so before we go though, I want you to go back and look at all the displacement graphs for acceleration, the 3 cases. And then what I want you to do is, if you had to write a sentence summarizing what's true always when something is accelerating for a displacement graph, what would you write? I'll pause to give you a chance to think about it. Okay, what you should have said is the displacement graphs for acceleration are always curved, or you might say they're always parabolas, saying the same thing. So whether they're curving up like this or curving like this, they have to curve, okay, to show acceleration. When it's like this, like the one in the previous video, that's a constant velocity, not speeding up or slowing down. Speeding up, slowing down, you have to have a curve. Now, go back and look at the velocity graphs and see if you could write a sentence about the pattern there. All right, I'll pause. Okay, what you should have said is that the velocity graphs are all linear, lines that either slope up or slope down. Maybe the t-axis is here. Maybe it goes like this, or maybe it goes like this. Or maybe it goes like this, or like this, but never across. Across would be a constant velocity. It's either increasing or decreasing. So it has to be a diagonal line for velocity graphs for acceleration. Last, go back and look at all the acceleration graphs. See if you could write a sentence about the pattern there. I'll pause to give you a chance to do that. Okay, what you should have said is all the acceleration graphs are horizontal lines. The t-axis might be here. It's either positive acceleration or negative acceleration. Never zero. That would mean constant velocity. Zero acceleration doesn't mean you're not moving. You might be. But if I'm going at 2 meters per second, 2 meters per second, 2 meters per second, I have zero acceleration. I'm not speeding up or slowing down. My velocity is not changing. Zero acceleration, steady. So that'd be that. But we are looking at positive or negative acceleration. And in real life, the acceleration could do this or even curve, but not in the Regents curriculum. Always draw horizontal lines for acceleration above or below the axis. All right, so that's it. And I guess I'll stop and I'll see you in the next physics video.